We're nearing the end of our discussion about linear dynamic systems and talking about the Laplace transform. And we just got through test one, which involves essentially deriving the differential equation, then utilizing the Laplace transform in order to go through and solve for V of s or I of s, whichever one we're looking for, and then bring that back into the time domain, with the inverse Laplace transform. The reason why we've spent so much time looking over that material is because it bridges the gap that between Chapter 8 and then Chapter 15 and 16 within our book. And what we're going to talk about in this lecture is the most generalized method that we can utilize for basically circuit analysis when we actually really care about that transient state when we do have a linear circuit that has resistors, capacitors, and inductors in it. And so you've noticed up until this point that everything that we've really looked at has just been derived series or parallel circuits based off how a switch flows over, and doesn't mean that everything for deriving those initial conditions were in that type of manner. Like sometimes we've actually had to use nodal analysis for it. But in this case, the reason why we just focused on that so much is because, again, it bridges that gap between Chapter 8 and Chapter 16. And I have found that students pick up Chapter 16 so much quicker because they already have that really in-depth understanding of what's really going on within these circuits, understand really what's going on with the transformation itself, the inverse Laplace transforms, obviously, which you did get in differential equations, but stuff with that in-depth knowledge with the initial conditions, it really segues into what Chapter 16 does for us, which really gives us the most generalized method that we can utilize for differential equation analysis for these types of systems. And if you look at Chapter 16, I highly recommend reading through Chapter 16. Don't even have paper in front of you. Don't write anything down. Just read. I mean, much of the book, the book has done those guys did a fantastic job writing basically good thoughts about how to approach each of the analysis techniques that we've seen with it, or talked about within any of the classes, whether it's Circuits 1 or Circuits 2. But what we're going to talk about right now is a really cool and unique concept of relating the Laplace transformation of the current voltage characteristics and then deriving a schematic model for that. And if we can derive a schematic model and literally transform that schematic into its S-domain equivalent, then we can actually utilize lots of the techniques that we've learned in Circuits 1 in order to basically just solve these systems with a lot more ease than we had before. And the nice thing about this is that this concept, by transforming the circuit into the S-domain, allows us the ability to solve much more complex and generalized circuits. And that's the reason why we spent so much time going through the full derivation of the differential equation and then utilizing the Laplace transform to solve it. It's because now we're at the most generalized method, and you guys are ready. Promise you're ready. So let's go through. Let's knock this out. What we did in the supplemental text is that I have taken example 1 from page 15, example 2 from page 18, and we're going to apply the concept that we're learning right now with this transformation method, and then we're going to actually solve with this method and see if we actually get the same form of VC of S for example 1 and then IL of S for example 2. And if we do, then the method works and we're good to go. So we're getting you guys ready for this most generalized method. And here we're just going to talk about some series elements. We're going to apply it also to parallel elements in a subsequent video, probably within a Microsoft Teams meeting. But in lab, we're actually going to do some loop analysis and really see how voltages can become a little bit more complex than what we've actually seen within this class up until this point. It's just we're at the really good stuff right now, and I love it. I love this material, man. So Laplace circuit element models, and we get those directly because everything that we look at is essentially KVL or KCL. We see that directly with VRT. VRT is that symbolism right there, the voltage across. And, Ohm's law could be a KVL equation essentially, because that means IR times IR of t is also voltage. Well, if we take the Laplace transform of that, there's no derivative in here or integral. It's very easy. VR of S is equal to R times IR of S. So in the S domain, we treat the resistor just like we do anything else. In the S domain, the current in the S domain multiplied by that resistance gives us the voltage in the S domain. Let's look here though. If we got VL of t for the inductor is equal to L times DIL of t dt, take the Laplace transformation of that, VL of S, which signifies a KVL equation directly, is equal to L times, in brackets, S times IL of S minus IL of 0. So you guys have already done that before. And that signifies right there a KVL equation. If we multiply through by L, then we actually have LS IL of S, that's a voltage, and L times I naught is also a voltage. If we rearrange the equation, we can rearrange it into a KCL equation. IL of S is equal to 1 over SL times VL of S minus IL of 0 over S. If we look down at the capacitor, IC of t is equal to C dVCT dt. Take the Laplace transform, we got a KCL equation right up front. IC of S is equal to C in brackets S VC of S minus VC of 0. So here, well, sure enough, CS VC of S is actually a current, and then C minus VC of 0, well, that actually itself is going to be a current as well. Sure enough will be. Definitely will be a current. Down here, and that may sound weird to you guys, thinking about the voltage here as actually being a current, or L times IL of 0 being up here being a voltage. But here, VC of S is equal to 1 over SC, KVL equation again, times IC of S plus VC of 0 over S. Sure enough, we have essentially KVL and KCL equations that we can actually go through and redraw a schematic model based off the initial conditions that we are given in the Laplace transformation, that we have to utilize within the Laplace transformation, because that tells us so much about what was going on with the circuit before the event occurred, whether that switch was opening or closing, or we just turned on a source, or removed a source, or put another one in. But here's the thing. Now remember with the second order differential equation, we had to have that change in that initial condition. And that change in that initial condition really gave us a lot of in-depth and intuitive understanding of what was really happening within the circuit. It's beautiful. Those initial conditions are so good. They give us that rate that really helps us understand how the circuit is going to start changing at that time that we switch over that schematic itself into a different schematic. Notice in each one of these, I even took out plus because we don't really need it, because VC of 0 minus is equal to VC of 0 plus, IL of 0 minus is equal to IL of 0 plus. Notice none of these don't have the change in the initial condition. So, once you start doing schematic transformations, you don't have to worry about that anymore. And I know some of you guys are going, oh man, I like the change in the initial condition. And you can go ahead and find those as much as you want. I would still do it, I do. But it actually simplifies the process, and we know from looking at a couple of other examples that even though that change in the initial condition may not be present for each one of these, That is still there because those change in those initial conditions were derived from evaluating that KVL or KCL equation at t equals 0, then applying that to the current voltage characteristic evaluated at t equals 0 plus. So it's still there. We just proved, and we proved that in a prior example. But here, we're going to redraw these circuits based off those KVL or KCL models. So as we said with the resistor, here, nothing, yep, sure enough in time domain, VR of t, and then we got IR of t and R. Switch that over into the S domain. In black here is the S domain. So plus to minus VR of S, and then IR of S, and then R. Nothing's changed. Look what happens when we look at the inductor, though. The inductor, once we move from the time domain down into the S domain, we tack on basically different forms of inductance here. It's S times that inductance. And then we tack on here that initial condition that's in the form of the voltage source that has a flipped polarity compared to VL of S. VL of S is made up of IL of S moving through SL, and then just as we saw from this equation over here, we subtract off the voltage polarity because here we're going from negative to positive based off the way that current's flowing. That's a voltage rise. So we take that off. So here we got L times I naught, and that signifies a voltage. If we go ahead and rewrite this in terms of the KCL equation, here IL of S is actually going to be made up of VL of S divided by SL plus, because that current will go down and will leave that terminal based off the flow, the polarity right here. And that current is actually going to be going down as well. So plus I naught divided by S. Let's take a look at the capacitor. Sure enough, here we have VC of t and IC of t. Oh, we're in the time domain? Nah. Let's go into the S domain. Come on now. Let's go into the S domain. So sure enough, based off the equation that we took the Laplace transform of, that current voltage characteristic, bam. VC of S is made up of IC of S multiplied by 1 over SC. And then here, same polarity, we tack on VC of 0 over S. Same polarity with that initial condition, forming a voltage source. Let's look at the current source variation of this. So here, IC of S is flowing in. We've got VC of S with that polarity. So to stay consistent with passive sign convention, here we would have basically IC of S, VC of S here. That current flowing through would be basically 1 over SC, and then divided by VC of S. Sure enough, that's what we derived over there. And then we also subtract off, because based off that polarity again, that current should be going down. So we subtract off basically C times VC naught. So the question that always comes up with these schematic transformations, I just gave you a lot of information right here, is which one do we use? Do we use the voltage source variation or the current source variation? And it just depends upon what you're looking for and essentially how you want to solve it. Either way actually works. It just, you have to have that good know-how of relating elements to each other, especially with current sources or voltage sources, in order to make them effective. But we're going to give two examples with example 1 and example 2 from page 15 and page 18 that kind of shows use of these specifically with the voltage sources. We're going to look at current sources at another time. But with the voltage source variations here of their S domain transformation. And we're going to use those to find the voltage across the capacitor for example 1, and then also look at the current through the inductor in example 2. All right, let's take a look real quick. And so again, guys, the whole entire point of this is just to see if by doing the schematic transformation, we actually, in fact, do get the same form of VC of S. So let's take a look here. So here we already know that we want to find VC of t for t greater than 0. Based off of that problem from page 15, we already had our initial conditions. VC of 0 plus is equal to 22.58 volts. IL of 0 plus was equal to 0 amps. So here, if I go ahead and transform the schematic over, we get here 1 over SC, we get V of 0 divided by S, we get SL, and then we get negative to positive L times I naught. So all we have to do right now, based off of that voltage polarity that we've been asked for, we're just going to go around the closed loop here and apply KVL. Sure enough, look at this. VL of S plus VR of S plus VC of S is equal to 0. But, let's see here, that's 3 variables in one equation. Well, may have to do some substitution here. We got VC of S. How can we write VR of S and VL of S in terms of VC of S? Let's do it. We already know what to do here. We already know what to do. We've done substitution before. We substituted the current voltage characteristics in the time domain back into the differential equation and manipulated that equation into a form of all VC of t. We're going to do the exact same thing but in the S domain, because we're going to take the current voltage characteristic of the capacitor in the S domain. We're going to substitute that back in for IL of S and IR of S. So here we expand VL of S into SL IL of S minus L times I naught. And then plus R times IR of S plus VC of S. Let's go ahead and substitute in IC of S because it's equal with series elements for IR of S and IL of S, and that's equal to CS VC of S minus C times V naught, the initial condition. And sure enough, in purple right here, SL, and then we substitute in IC of S for IL of S, CS VC of S minus C V naught minus L times I naught, plus R, and then in brackets C S VC of S minus VC naught for IR of S, plus VC of S is equal to 0. All we have to do now is just rearrange this equation directly. Just rearrange it directly. S squared times LC VC of S plus RCS VC of S plus VC of S. Congratulations, guys. We got it all in the terms of one variable, what we were looking for, substitution, just like we did in the time domain. And that's equal to RC V naught plus L times I naught plus SLC times V naught. Well, if we go ahead and isolate the highest order derivative, essentially, in the S domain, where we have S squared, man, RC divided by LC, that gives us R over L. And then we get 1 over LC times VC, and then everything on the right-hand side will stay consistent with how we derived it also, how those equations were derived in the S domain when we utilize the differential equation from the time domain. So sure enough, we get S squared plus 10S plus 25 times VC of S. That's the same characteristic equation that we saw before. And then on the right-hand side, S times 22.58, and then we had 10. Sure enough, we had 10 times 22.58, which was what RC was equal to, and sure enough, there we go, right there. We got 225.8, and then obviously I naught was equal to 0, so that went away. Divide through and isolate VC of S and solve for it. S is equal to S times 22.58 plus 225.8 over S squared plus 10S plus 25. Guys, we got a critically damped system here, and we know how to solve this, and this is the exact same form of VC of S that we actually gained from deriving the equation in the time domain and then looking at the initial conditions, taking the Laplace transform and solving for VC of S. And from here, we know how to actually get back into the time domain with partial fraction expansion as well as the inverse Laplace transform. But you guys should be satisfied with this and be like, oh, yeah, Mr. Morley, yeah, we got it. We're going to move forward. No. What about that current, though? Well, if we were just concerned about the current, we know that IL of S is equal to IR of S is equal to IC of S. You probably are thinking, because I know you're thinking ahead, what if we just expanded that equation in terms of the current voltage characteristics in the S domain, or basically just going around the closed loop and applying KVL, looking at the current voltage characteristics in the estimates in the schematic way, and then just go ahead and just solving the current directly. I know you're thinking it. Let's take a look. All right, so in example 2, just like we did with the overdamp case for the inductor current on page 18, we're just going to do what we did before. We're going to go ahead. We already know that the initial conditions for that problem were VC of 0 was equal to 0 volts, IL of 0 was equal to 2 amps. So we're just going ahead and take the circuit right here. That's the switch that was closed over, obviously. We're going to convert that, just like we did right here, into its S-domain schematic. We know that that current was going down, flowed down here. We know that that initial current flowed down through that inductor, and then, obviously can't change direction instantaneously. We know that. And so here we went ahead and stayed consistent with how the circuit was derived. So here we get SL and then negative to positive, L times I naught. Remember, polarity for the resistor is dependent upon current flow, so we're going to see that too. Here, that voltage was actually 0, and then, well, that was the initial voltage across it. That's what I meant to say, sorry. So this is eventually going to go away, and we don't even have to worry about it. So we're going to see that in just a sec. VL of S plus VR of S plus VC of S is equal to 0 volts. Expand that out by the current voltage characteristics, and sure enough, we go around the closed loop here. SL times I of S will actually give a portion of VL of S, and then minus L times I naught. Notice how in brackets here I go ahead and keep VL of S, because VL of S, if we just look here and say that I of S multiplied by SL is actually going to be that VL of S. No, it's not. We have to take in consideration the initial condition. That's why I go ahead and put it in brackets. But we're still going around the closed loop here. SL times I of S, and then here we basically subtract off L times I naught for that voltage. Plus R times I of S, sure enough. I of S, and even though I just had I naught right here, we know that we can use that to show the initial direction that we're actually utilizing, but we're still actually utilizing that direction for I of S as well. And sure, R times I of S, and then plus IS times 1 over SC. That's basically that model now for the capacitor, 1 over SC times I of S, but the voltage isn't complete unless we tack on that other voltage source, plus VC of 0 times S. Okay? Sure enough. That's what we would expect to see there. And so here, ooh, that's actually backwards right here. Yep, and I think that was backwards as well. So sure enough, if we go ahead and just start, parsing out this equation, we obviously know that S is in the denominator. We need to get rid of that. So we're going to take the whole entire equation and multiply both sides by S. Here I just moved over the initial conditions to the other side. And so sure enough, here guys, we actually got, it's exactly what it was. So S squared times L times I of S plus RS times I of S, and then plus I of S divided by C, and that's equal to SL times I naught, and then minus VC of 0. So we go through and divide through by L. We isolate that highest order. S squared times I of S plus R over L times S times I of S. That's what we're looking for. Plus 1 over LC times I of S. That's exactly what we look for, guys. And then here we get S times I naught, and then minus VC of 0 divided by L. VC of 0 goes away. We go ahead and put in our variables for R and L, and then also C. And then we get basically exactly what we were looking for, guys. I of S, sure enough, is equal to S times 2 over S squared plus 10S plus 9. Congratulations, it's the same thing. And again, want to make sure that we put this in here correctly. Here, that actually is going to be positive to negative in that orientation. So I apologize for that. But this example perfectly describes exactly how we would actually treat a problem like this if we were just looking for the current. We just simply just go around the closed loop and literally just, we could either just expand this out by knowing VL of S and VR of S and VC of S, or just look at the schematic and apply the schematic to the equation and start crunching. Once we get down to I of S, we know what we need to do. Partial fraction expansion, find basically those coefficients. Let's get those simple terms back into the time domain. All right, guys, we're going to see how we deal with this with parallel elements, and then we're going to get into the way more complex circuits. And that's when the fun really starts. So, I'll see you guys next time. I'm going home to eat. I'm starving. It's 8 o'clock here.